Let's look at the difference between physisorption and chemisorption. So really, in short, the difference is right there in the name. So one is a physical process where molecules are stuck to the surface, and the other case is a chemical reaction between molecules, the adsorbate molecules in the surface. So let's look at some of the differences. So first of all, let's look at what kind of interaction is it? So what's the bonding? So the bonding in physisorption is just going to be a van der Waals interaction. And in a chemisorption, it's going to be a covalent bond. If we look at the energy involved, in both cases, it's going to be a negative delta G for the process, delta G standard for the process. In one case, though, it should be small, less than 60 kilojoules per mole. And because the chemisorption involves making and breaking covalent bonds, it's going to be large. It's going to be greater than 60 kilojoules per mole. And so because we're doing a chemical reaction in chemisorption, we expect that we will break bonds in our adsorbate molecule, whereas in physisorption it should stay intact. Because it's a chemical reaction for chemisorption, we will have an activation energy very often. We will not for physisorption. And with the physisorption, we're just sticking molecules to the surface. So we can stick a molecule to the surface and then add another layer. So we could have multi-layers. It's possible anyway. And with chemisorption, because it's a chemical reaction with the surface, once the surface is coated, it can't react anymore. So there's only going to be one layer. So those are the main difference between physisorption and chemisorption. We can draw this in terms of potential energy diagrams. So we've got Z, the distance from the surface, and E, potential energy. And we'll draw this curve separately first. So here is the potential curve for physisorption. So we have a shallow potential well, and eventually the molecules, the adsorbate molecules, electron clouds will crash against the electron clouds on the surface, and so it goes up. If we look at the curve, so this is physisorption. So imagine something like a hydrogen molecule interacting with platinum. It can undergo a simple van der Waals attraction, but once it gets close enough, it can break apart into two hydrogen atoms and bind chemically to that platinum surface. And so that's shown sort of schematically over here, where we have the broken bits of molecule in red representing chemisorption and the intact molecule in green representing physisorption. So let's draw a potential well for the chemisorption side. We've already drawn it for physisorption. Well, first of all, we're going to have a much stronger interaction for a chemical bond, which means a shorter bond, and the potential well will be deeper. So in this case, the potential well, as we pull the molecules off, ends up at a higher value because we're pulling these off as individual atoms. So there's the energy difference between two separated hydrogen atoms and a hydrogen molecule. Of course, that's higher in energy. So we have the separated molecules here, and we would have an intact adsorbate molecule out here. All right, well, if we combine these graphs, we can see that when we draw the overall energy curve, just potential energy versus difference, we have to sum the two different types of interaction, the physisorption reaction and the chemisorption process as well. When we add those two curves together, we can see that we're going to get a curve with two different wells, a little well for physisorption and then a deep well for chemisorption. And notice the maximum here is going to depend on the numerical values of these two curves. We can end up with a curve that looks like this, where we actually have the potential energy go through a maximum above the zero of potential energy. So here we have a physisorption well the molecules get close enough they can fall into a chemisorption well. Notice that there's actually an energy barrier to chemisorption in this case. So over here we can slide down into that well. Here we have to actually supply energy if we want to fall down to this well. So there's actually an energy barrier to adsorption. So this is called activated adsorption. So at low temperatures, the molecules would physisorb, but they wouldn't actually react with the surface to do chemisorption. So it's kind of like the activation energy for a reaction.